this lecture series, we're going to cover the solar system. When we talk about solar system formation, I'd like you to go ahead and take a look at this website. I'll have the link available for you in the course. It's kind of neat, and it gives you some videos of the solar system. Okay, so let's talk about the solar system from when I was a kid. We have our four inner planets: Mercury, Venus, Earth, and Mars. We then have the asteroid belt. Notice this is not to scale. Jupiter is not sitting that close to Mars. And then we had the gas giants: Jupiter, Saturn, Uranus, and Neptune. And then we also had Pluto, which was considered our last planet, the ninth planet. This is the solar system that we have today. We still have our four inner planets, our four outer planets, but Pluto has been classified as a dwarf planet instead of a planet. There are a lot of reasons for this. We have found multiple objects beyond Neptune. They all seem to cross Neptune's orbit. And we also have Sirius, which is a spherical object sitting in the asteroid belt. So it just seemed to make sense to classify Sirius, Pluto, and Eris, which is in this diagram, 2003 UB313. It just seemed to make sense to reclassify these under a different category called dwarf planets. When we start to look at the characteristics of Pluto and Eris and all of the other dwarf planets, you might agree with what the Astronomical Society has done. Okay, so let's talk about the different parts of our solar system. We have the sun sitting at the center. We have the terrestrial planets, then the asteroid belt. The asteroid belt is actually fairly large in width. Then we have the Jovian planets, the Kuiper belt, and the Oort cloud. Here are the ingredients of our solar system. 99.8% of the mass of our solar system is located in the sun. 0.1% is in Jupiter. All the other planets added together is 0.05%, and 0.05% is also everything else. That would be your comets and your asteroids and your debris beyond the inner part of the solar system. So let's talk about the sun, which is at the center of everything. It's a middle-aged average star. It's made mostly of hydrogen and helium. 99.8% of the solar system's mass is in the sun. We know that from calculations of what we've done, that the age is about 4.6 billion years old. It shines because the center has fusion taking place, which we've already covered. Again, the surface temperature is about 6,000 Kelvin. It's mostly visible radiation with UV and infrared. And it also will shine for about 12 billion years. The sun definitely dominates the solar system as far as size and as far as mass. If you take a look at this picture, you can see how large the sun is compared to the largest planet, which is Jupiter, and then the very smallest at the bottom end, which is Pluto. In fact, you can't even see the dot that represents Pluto. That's how small it is compared to the sun. For our terrestrial planets, there are four. It's Mercury, Venus, Earth, and Mars. They tend to be rock-like planets, so they have high densities. The largest of the terrestrial planets is Earth. They are only in the inner solar system between 0.4 and 1.5 astronomical units. And remember, an astronomical unit is equivalent to the mean distance between the sun and the Earth, which is 93 million miles. They have solid surfaces, mostly made of silicates and iron. They have a high density. The densities of these inner planets is above 5,000 or more, and rock sits between 2,000 and 4,000. So you see there has to be some type of heavy metal involved in the terrestrial planets. Out of the terrestrial planets, all of them have atmospheres. However, Mercury's atmosphere is very thin, and it's actually moved around by the solar winds bombarding it. So here you see the size of the planets. The mass of all of the planets is less than that of the Earth, where Venus is close with 0.82 or 82% the mass of the Earth. Mars is only 11%, and notice how small it is compared to our Earth. Mercury is the smallest of the terrestrial planets at 0.055 Earth masses. Now let's talk about the Jovian planets. Jupiter, Saturn, Uranus, and Neptune are your 4 Jovian planets. They are the largest planets by at least 15 times the mass of the Earth. They are only located in the outer solar system from 5 astronomical units to 30 AU. There is no solid surface on any of the 4 planets. They're mostly made up of gas. They have very, very low densities. In fact, Saturn's density is so low that if it could fit in a bathtub, it would float. The 2 gas giants are called Jupiter and Saturn. They're all gas giants, but Uranus and Neptune have a lot of ice as well, and that means that we call them the ice giants. Okay, so Jupiter and Saturn are mainly hydrogen and helium. As you go further and further in, it becomes liquid hydrogen, and then you have a core. The ice giants, Uranus and Neptune, actually also contain methane, which gives it the blue color. And here are your Jovian planets. Jupiter is the largest, Saturn is the second largest, and then you have Uranus and Neptune, which are close in size and color. If you take a look at the comparative sizes, you can see how large these gas giants are compared to the inner planets and also Pluto. Let's talk about dwarf planets. Dwarf planets were defined by the International Astronomical Union in 2006. Here are some of the dwarf planets. Ceres, which was first considered a planet, then it was considered an asteroid. It was actually discovered in 1801. Now it's been reclassified as a dwarf planet. Pluto is what we call a trans-Neptunian object. That means it crosses the orbit of Neptune. It was discovered in 1930. Eris is also a trans-Neptunian object. It was discovered in 2005 by Michael Brown's team. Haumea is a trans-Neptunian object, or at least we believe it is, and Makemake is also believed to be a trans-Neptunian object. Here you can see a diagram of the dwarf planets. We also have in this diagram a picture of Luna, our moon, and the Earth. If you look at Haumea, it actually appears to be elongated or an ellipsoid. This is due to its high rotation rate. That causes it to become elongated. It spins very, very quickly. Pluto and Charon are actually believed to be a binary system, where they actually go around each other instead of one orbiting the other. Eris has a moon called Dysnomia. Pluto actually only shows 3 moons there. I believe it has 4 or 5 now. Okay, our moon is called the moon, Luna. Jupiter's moons, the 4 largest, are called the Galilean moons. That's Io, Europa, Ganymede, and Callisto. Saturn's largest moon is Titan, and Neptune's largest moon is Triton. Sometimes this gives students trouble. They both start with T and they end with an un. So here's how I remember it. Neptune carries the Triton. Saturn is the father of the Titans. Okay, so if you just remember that Neptune carries the Triton, then that's going to clear it all up for you. Many, many moons surround Jupiter, Saturn, Uranus, Neptune. They all have many moons. The inner planets have very few moons. Okay, Mercury and Venus have no moons at all. So out of the 4 terrestrial planets, only the Earth, which has 1 moon, and Mars has 2 moons. They are the only 2 terrestrial planets that have moons. Okay, so here are the giant moons in the solar system. Ganymede is the largest. That is one of the Galilean moons. Titan is Saturn's moon. Triton is Neptune's moon. Callisto, Io, and Europa are again 3 of the 4 Galilean moons. Okay, so here's the larger moons with also a picture of Mercury and Pluto. So you can see Ganymede is actually slightly larger than Mercury, and quite a few of these moons, in fact, all of these moons, are larger than Pluto. If we add in some more, you can see that Ceres, which is right here, is actually quite small compared to some of these other moons, but it's been classified as a dwarf planet. Okay, and here are some more moons. You see, here is an asteroid, and here is an asteroid. Scientists looked at both Vesta and Pallas to see if they would be large enough to be dwarf planets, but they're not. They do not have an actual spherical shape. All the rest are, I believe, moons of either, well, they're all part of the Jovian system, the Jovian moons. So it could be, let's see, we have some from Saturn, some from Neptune, some from Umbriel, I believe that would be Uranus. And so you can see there's moons from all of the gas giants there. Okay, let's talk about the Kuiper Belt. The Kuiper Belt actually, we believe, sits outside of the 8 planets. So it's a class of icy bodies that orbit beyond Neptune. In fact, it's slightly beyond Pluto. It's only found in the outer part of the solar system, greater than 30 astronomical units. We believe that most of the objects in the Kuiper Belt have densities of about 1.2 to 2 grams per centimeter cubed, or about 1,200 to 2,000 kilograms per meter cubed. We believe that that's close to, or it is close to, the density of ice or water, which is 1,000 kilograms per meter cubed, or 1. And 2 to 4 is rock. So it could be that this is mostly ice with bits and pieces of debris that are rocky materials. So it could be just dust particles or dirty ice, another way to call it. Some examples of some icy dwarf planets would be Pluto and Eris. The Kuiper Belt objects, again, are going to sit between 30 and 50 astronomical units. Charon, Pluto's largest moon, would also sit in the Kuiper Belt since it orbits Pluto. Sedna and Quaoar are actually considered Kuiper Belt objects and not dwarf planets. They're distant icy bodies that were discovered by the same group that discovered Eris. So here you can see a picture of the Kuiper Belt. It sits right at the boundary of Neptune. The Oort cloud is theoretical. It's believed to be a spherical cloud of the comets. It extends out to almost 50,000 astronomical units, or 1 light year from the center of the sun. It may contain trillions of comets. The outer edge is the farthest reach of the sun's gravitational pull. There is no confirmed view or observations of the Oort cloud. It's way too far out. But we do know that these comets that come in, based on their trajectory and based on their speed, we know that they have to go pretty far out. And it could be that they could extend all the way to 50,000 astronomical units from the sun. So this is the theoretical Oort cloud. If you look at the picture right here, this picture right here, sorry, let me write it in yellow so you can see it. This picture right here of the inner solar system and the Kuiper belt actually sits right here in the Oort cloud. Okay, so the Oort cloud is believed to surround the solar system and the Kuiper belt, and we believe this is where all the long-term comets reside. Okay, so what else is there? Well, there's actually leftovers, and those would be your asteroids, your meteoroids, and your comets. The asteroids are made of rock and metal. They have densities between 2,000 and 3,000 kilograms per meter cubed, or 2 to 3 grams per centimeter cubed. They are about 100 kilometers to the size of large boulders. They can be found in the main asteroid belt between 2.1 and 3.2 astronomical units. There are asteroids that sit around or orbit planets. There are also asteroids that sit in specific locations on the orbit of Earth and Mars and Jupiter. The meteoroids are bits of rock and metal. They can be the size of grains of sand up to the size of boulders. And these are things that reside in space. They can also be bits and pieces broken off from collisions between other meteoroids colliding with the surface of a planet and bits and pieces of that planet breaking off. Comets are composed of ice and dirt or rock, and we call them dirty snowballs. They have long tails of gas and dust that are swept away from the sun as they come near to the sun. So as the comet comes close to the sun melts that ice and debris. The dust goes out and the light from the sun reflects off of it and it glows. And then also the gas that's emitted gets hit by the electromagnetic radiation of the sun, and that energy is absorbed by that gas and re-emitted, and that causes the gas to glow as well. So sometimes, if we're lucky, when a comet passes by, we can actually see two different tails. One would be the gas tail and one would be the dust tail. Okay, so here are some pictures of some asteroids. I love Gaspra. I don't know why. It's just my favorite one. Okay, a meteor burns up in the atmosphere, and that's what we call a shooting star. A fireball is when it glows extra, extra bright. When it actually hits the ground, it's called a meteorite. And here on the right-hand side, you can see two different types. Here we have the stony meteorite, and here we have the iron meteorite. Okay, here are some pictures of comets. This is Halley's Comet, and here you can see a bit of the glowing factor that happens. This is a comet here, and here you can see little bits and pieces that have melted off and have come off due to impacts. So it just looks like a big ball of dirty ice in space. Okay, slide, you're not necessarily going to be able to see the numbers, but one thing I want to point out is this. If Mercury were 1 inch away, then Eris would be 295 inches away. So that kind of shows you the size of everything. It's extremely large. Another thing I want to point out is the year. It takes 557 years for Eris to go around the sun once. That's incredible. I mean, that is well beyond anything we would know. I mean, here we are at 365 days. Mars has a 687-day year. Jupiter takes 12 years to go around the sun. Pluto takes 248 years to go around the sun. So these are pretty large numbers when we talk about things. Okay, so is Pluto a planet? What do we consider when we talk about a planet? Do we consider its size? What about its shape? How about its orbit, where it goes? How about what it's made of? Well, these are all really good questions and really something we need to consider when defining a planet. And up until now, we haven't defined a planet, or at least up until 2006. So that's been a real problem. How do we classify something as a planet or not a planet if we don't know what a planet actually is? Okay, so in 2006, the International Astronomical Union came up with its own definition of planet. And they had to do this because we were discovering more and more things beyond Neptune. So if we're discovering more and more things, we need a definition of planet. Is it a planet? Is it not a planet? What makes a planet? So they came up with this definition. Number one, it must orbit the sun. So any object that orbits the sun can be classified as a planet, at least at this point. Next, it has to have enough mass in order for it to stay spherical in shape. Okay, so it can actually become a little bit flattened. We call that oblateness, and that's due to the planet actually rotating very quickly or due to it being made of gas. So the gas giants actually are oblate, meaning that they actually look like they're a beach ball that's kind of been squished a little bit. That's okay because we know that's due to the rotation. But the actual mass that's there could form a sphere if it wasn't rotating. Okay, so that's the thing. It has to have enough mass to have a spherical shape. The last thing is, and this is the key here, has cleared the neighborhood around its orbit. Okay, Pluto crosses the orbit of Neptune. Some people may say to me, well, wait a minute, doesn't Neptune cross the path of Pluto? That may be true, but Pluto spends more time outside than it does inside. And that means it's crossing Neptune and not Neptune crossing Pluto. Okay, Neptune's orbit is clearly within Pluto's orbit. Okay, so the last thing is it can't be a satellite. Okay, so it cannot orbit another object, it can only orbit the sun. Now, what is the definition of a dwarf planet then? Wait till you see this. It must orbit the sun. All right. It has to have enough mass in order to be spherical in shape. Okay. Here we go. Has not cleared the neighborhood around its orbit. That means that it is actually crossing the orbit of another planet or another object. But it can't be a satellite. Notice here there's only one thing that's different between a dwarf planet and a planet. Okay? When people say dwarf planets are not planets, that's true. By definition, a planet is specified as clearing the neighborhood around its orbit. Dwarf planets have not. Does that mean it's any less significant? No. It is just as significant as the other planets. And that's why we've created a separate category. The other thing is that scientists like to put things in boxes, to categorize them, to put them all with the same stuff, right? If I gave you a room full of children and I asked you to sort them, you may sort them by their hair color, their eye color, whether they're boys or girls. Put the tall kids on one side, the short kids on the other side. We love to classify. And so this gives us a way of classifying Pluto with other things just like it. And that makes me, as a scientist, feel better, knowing that Pluto is no longer that odd guy out, the one that doesn't fit the mold, the one that just isn't like everybody else. Now he is. And that's what I love about what the IAU did in 2006. By giving us these definitions, it allows us to reclassify the objects into categories that suit it better.